Greetings and welcome to a new video about another mechanical system problem. This is our second example considering the rotational mechanical systems and the fourth example in this series having the dynamic systems playlist. So what we have in this case is a system which has two dampers and one spring and two inertias in the rotational manner. So again, we will look at the calculation step by step and also verify these in simulations using Simulink and Simscape and MATLAB. So let's look at our situation. In this case, we have a system. It is a rod supported by a bearing at two ends, and it's also undergoing torsion. So this is the script given here in a pictorial view. So we have this rod, and there are two bearings at the left and right hand side. So we have the torque applied, and we have also the theta 1 and theta 2, which will be then determined later. There's also torsion here, which is also one of the parameters in our system. So what we want, or what's happening in this system is the following. The torque T is applied, and we would like to measure or calculate or determine the angular displacement theta 1 and theta 2. So that's actually what's happening. So we would like to also have a model of this system in order to calculate these theta 1 and theta 2, because this is all merged in one block. So we would like to split it up. So that will be helpful. So let's then model this rotational mechanical system with two masses, because we have sort of a separation between theta 1 and theta 2. And also two dampers, because there is a damping here because of this bearing. And of course there's a spring. There's a rotational spring there. That can be, of course, sort of an interaction or interconnection between the left and the right hand side. So the model can be then described as shown here. So we have this mechanical reference on the left side or also the right side. This damping B1 and also the damping B2 is just due to these two bearings. And we have split actually this mass into two separate masses of equal, let's say, value. And we have also the same moment of inertia J1 and J2. So we have this exact same inertia, and we have a torsional spring here, which is then due to that rotation. Now we see the torque and also the theta 1 clearly on the left side and the theta 2 on the right side. That is the K for the spring, the B1 and B2 again for our damping. So again, in the previous videos, we like to calculate or determine our transfer functions going from the torque applied all to the theta 1 and then also the torque applied to theta 2. So theta 2 over torque is our G2, theta 1 over torque is our G1. Okay, so how to work out this? Again, we start with the differential equation. And for this case, since we have a rotational system, for rotation, we can use the Newton's second law for translation, but in this format using the rotation. So instead of having mass times the second derivative of the translational motion, the x, now we have the moment of inertia times the second derivative of the angular displacement, which is then equal to the summation of the torques. So in this case, it was the summation of the forces for our translational system. So this is quite very similar to what we had for translational system. Now moving on, and then considering actually each rotation one by one, we can say now for one rotation 1, or the inertia one, I must say, we can say, okay, this inertia here has this value, so J1 times the second derivative of the theta 1 will be then equal to all the torques applied on this part of this system, which is of course a torque, because that's applied on this side and it's also in the same direction. That's why we have a plus at the left side and also plus at the right side. The bearing will fight back, so it's actually minus B1 times the first derivative of the angular displacement. We have also this spring will fight us, but also the theta 2 is there. So theta 2 is sort of helping us in the positive way, and theta 1 is actually fighting back. So there's actually net displacement, angular displacement, and we have minus K times the difference between these two faces, or I mean the angular displacements. That's for the inertia J1. Now for J2 in a simpler form, of course you look actually at this point. Now we have the J2 times the second derivative of this angular displacement. Now we'd like to also check what is fighting back and what is actually going in the same direction. B2 is fighting back. We're using the first derivative, the theta 2, which is actually shown here. Also the spring is fighting back. And in the same manner, we have the theta 2 as our reference direction. So theta 1 is actually sort of helping also. That's actually subtracted from this theta 2. And now we have the complete differential equations for our inertia 1 and also inertia 2. Okay, now we would like to, of course, transform this in the Laplace domain such that we can easily work out this in the S domain instead of using this time derivatives in the differential equations. So let's do that for the inertia J1. Now we know and we assume the initial conditions are all 0, so we can then replace each derivative by an s. So if you have a second derivative, you just replace it by s squared. If you have a first derivative, you do that as an s. If you have no derivative at all, you just take it over, but you replace the t by s. You do that actually at each label. So we have then J1 times the s squared theta 1 s. So that's actually for the first, for the left side of this first inertia. And then moving on the right side is a similar form. So you see actually the first derivative is the s, and you see in this manner the same thing here. Now we can replace this in this form, so we can place all the elements which has something with theta 1 to the left side, so we can group them together. And the torque is then on the right side, and also the theta 2 is also stay in there. So we have now this equation, and we can also now group these elements. So J1 times s squared plus B1s plus k, all of them times the theta 1 is equal to torque plus k times the theta 2. Now that is fine. Now we can set parameter that will be helpful later on, and also which will be easily worked out for our future analysis. We can say this part is delta 1. So that can be then this, and it is also much easier to read now. The delta 1 times the theta 1 is equal to torque plus k times theta 2. Now we can now work this out in this form. So we have now our first equation. We will use this later for the future analysis and also determining for the transfer functions given here, G1 and G2. Okay, moving on, and then going to inertia 2. Again, going from here to the Laplace domain in a similar form. Again, the first derivative and the second derivative get all another s. So you have this expression. Now group all these theta 2's together, so, and then move them to the left side, so you have actually this. And also make this parentheses complete, so it's in this case as similar as this one. Now we can again set a new parameter, let's say delta 2, which is then this, which is between the parentheses, and then call this delta 2 times the theta 2 is equal to k times theta 1. Now we have a nice expression. We can now say, okay, let's make this equation number 2, but you can of course also rewrite this in a form that theta 2 is expressed in the terms of theta 1. Or, and then call that equation 3, or you can say, let's make now this also theta 1 in terms of theta 2, which is actually shown here. And this will be then also called another equation, so that's equation number 4. So we have now 4 equations, and we would like to now use these 4 equations in order to determine G1 and G2. So let's move on. We have now this equation. You can see here that equation number 1 and equation number 2 and equation number 3 and equation number 4. Okay, what we do is the following. You actually start with substituting equation number 3, this one, in equation number 1, in this one. So what we have is then the theta 2 will be replaced by this expression, k over delta 2 times the theta 1. So what you get is the following. Of course, you get a k times k, so k squared in the numerator here, over delta 2 times theta 1. And you can see that the left side has now only theta 1s as a parameter, and the right hand side is only the torque. So we can now group this together in the next step. And also we can do it for the later for the substitution for equation number 4 and 1. But let's group them together here. Or first, of course, left hand side and right hand side multiplied by the delta 2 will be helpful to work out this easily. And then group them together, you will have this expression. What you see now is, if you now express the theta 1 over the torque, you will get the delta 2 over delta 1 times delta 2 minus k squared. You can of course check this by cross multiplication of this expression, so you can see delta or theta 1 times this, which is actually shown here, is equal to delta 2 times the torque, which is actually shown here. So this is indeed correct. Now going on to the next one, which we have now the G1, by the way. So we have actually determined the first part of this problem. Now in the second step, we can now say substitute now this equation in here, so that you can only have the theta 2 in your expression, also torque, because that's actually what you want. You're actually heading to an expression which has only theta 2 and torque. And in this case, you would like to only keep the theta 1 and the torque in your equation. Now let's then move on and then say, okay, this is what I have. If I substitute this 4 in here, which is then this, will be replaced. So you get theta 1 times, the delta 1 times delta 2 over k, which is actually shown here, and a minus k times theta 2 is equal to torque. Okay, now let's again multiply left hand side and the right hand side by k, and we have now this expression, which is now easily seen. Now collect them together, we have this term here, and also using again the expression theta over torque, so in this case theta 2 over torque, we get k over the same expression as this. That's of course not a surprise, because you need to have the same characteristic equation for your system. If you look, for example, theta 2 or theta 1, must not have any effect. It must have the same characteristic equation. Of course, it will have a different numerator, and also that will cause, of course, if there's any zeros. So in this case, it's just a constant, and in this case, this of course the delta 2, which has some dynamics. Okay, this is now our G2, and that's actually also what we wanted in the second part of this problem. So moving on and then work it out in great detail, what we have is, of course, delta 2 can be just taken from this setting, and also delta 1 and delta 2 again also shown here, so you can make it actually now complete. And that also counts for the G2. Now we have actually the complete transfer function instead of using delta 1s and delta 2s. Now, if we now move on and look at this a little bit carefully, because this is what we have for G1 and this is what we have for G2. If I now work out these parentheses, I will get a lot of terms, and collect them together, you will get actually a fourth order system or fourth order polynomial. What's interesting here is, if you work it out up to this point, you will get a k squared also as a constant. But we have also a minus k squared outside these two terms which are multiplied. So you'll lose actually your k squared. But that means actually that this will go, and you only have here as a polynomial in, let's say, as a multiple of an s. So that means you have a pole for this G1 system at the origin. So that means if you apply a step at this system, you will have a ramp response, so that will increase linearly. Doesn't actually settle to some value or steady state point. So that's interesting to see here what's happening if you have a different input signal. Now the same counts for G2 also. If you go down, you can see this is then of course also the same quadratic equation. And again, we have now a pole at origin. That will again give you this response for a step input. If the torque is a step input, which is in this case the situation, then we will have a ramp, sort of a ramp response or linearly increasing response for our angular displacement. So that's interesting to notice here. Okay. Let's then move on and check our Simscape results. In Simulink, we can draw our mechanical system using Simscape elements. So we have actually this all here. So this is our step input torque, which is 10 Newton meters. Actually, all the values for this system are also shown here. So let me go one by one what's actually shown here. This part is actually to move from the Simulink signal to the physical signal. So you actually need to first this, and then you enter the domain of the mechanical system or mechanical domain. This is an ideal torque source, so that is sort of the torque which you apply here and then changing that in the mechanical domain. We know that we had a damper here that was going to a mechanical reference point, so that's actually what we have here. In series to that, we had an inertia, and then in between there was also a spring, and then another inertia, and then also another damping that will also go to the mechanical reference. So this part is the system we have, these 5 elements here. Now we need to measure, of course, the angular displacement here and also the angular displacement there. You do that by using the ideal rotational motion sensor. Of course, we need another one, so that's actually also shown here, and we also need a scope to measure this. Now, before we can do that, we need to go back from the physical system to the Simulink. So that's also a conversion from the physical signal to the Simulink. And then apply now the input completely to the scope directly, and also our angular displacement 1 and also the angular displacement 2. So we get 3 grams from this. Now, for sake of discussion, I have picked some values for inertia. So I have to say, okay, it is of course the same element, and we just divide it in 2. You get the exact same inertia value, and I've just chosen 500 kilograms times square meters. The damping coefficient I've just chosen as 100 Newton meters, same for the left and right hand side, and also that spring constant just as 200 Newton meters per radians. That's just a value to have some idea and also see the plot, otherwise it will be too symbolic and you don't see much happening. Okay, now let's then check the response for the displacement θ2 in Simulink. Now this is what we have. If I apply 10 Newton meters, you can see that here as a torque. The green one is the displacement 1, and the yellow one is the displacement 2. You can see indeed that due to that step input, the output is not really constant anymore. It will linearly increase. It will, of course, start a little bit with a different slope, but at some point it will catch up and then has a constant slope. You can see here that, for example, at 150 seconds, it has 7.26 radians, but at this point, let's say at this time, 205 seconds, it has then 10 radians as a value for our displacement, angular displacement. So it's sort of the unity gain for this part at 205 seconds. Of course, if you move on to higher values for your time, this will just increase. So you can see there is no ending, and that means if you just apply a 10 Newton meters torque at the input, this will just go on, and it will also the same for the yellow one. So you can see for the yellow one, in a similar form, again it has some value for it, let's say on 150 seconds. I just picked that randomly, and also you can see that at 206 seconds, approximately 206 seconds or 1 second, a little bit higher than the other one, is again 10 radians per second. You can also see it here from this label here. Now, okay, if I now a little bit zoom in this part, we can also see more in detail. But before we do that, let's also check the script. This is the script we have. In order to plot the body plot, and I mean the step response for this system, we can also have a script here and then make that also visible using the command window in MATLAB. So this is again the J1 and J2 for our inertias, and also the B1 and B2, and also the K for our spring constant between the two inertias. Now these are the D2 and D1, which is actually delta 1 and delta 2. These are the transfer functions, and these are the input and output signals. So the torque is 10, and we have now Y1 and Y2. Y1 is inputs your G1, your first system, times your torque, and Y2 is the second system times your torque. So now let's then check our responses for this situation. Now the component values again for future reference. The T is actually our torque, so that's the blue line, it's just 10. And then the Y1 is our response. You can see it is a linearly increasing line. So again, some values here to designate that this is indeed linearly increasing. You can see also that from, let's say, 50 to 150, so it is actually going up by 100 seconds, you're increasing your amplitude from 2.26 to 7.26, so it's actually going up by 5 radians. This will of course increase in linear fashion, so if you go from 150 to 250, you get approximately the same increase in your radians, your angular displacement. Okay, now let's also look at a θ2. Again, the plot for your response. Again, the same values, and you see again a blue line, and again some labels here. You can also see the 50 seconds, also 150 seconds, again 2.24, in this case a little bit smaller in amplitude. It was 2.26 in a delta 1, and this is then 7.24, so again 5 radians difference. So we go up by 5 radians as an angular displacement if we go up with a time of 100. So 100 second difference will give us 5 radians difference, actually increase. So 5 over 100 seconds is a 0.05 radians per second. You can actually say also that is sort of your angular velocity in order to calculate that. Now, if I want to also zoom in a little bit closer to the delta 1 and the θ1 and θ2, and see also the difference between them, we can of course zoom in and part and label, let's say at 150 seconds, what's happening. At 150 seconds, we see the Y2, which is the response to the of the system G2. It is 7.24. So this is the angular displacement θ2, and this is the angular displacement θ1. So the yellow one is the θ1, let's say the dark orange one is the θ2. Now the yellow one has a value of 7.26 at 150 seconds, but the other one has 7.24. So that's a little bit of difference. So that's actually what we get from this analysis. Again, for an input torque of 10 Newton meters. Now, of course, you can take different values for here and then try to plot another response. What you for sure will get is the ramp response. So it is not possible in this case because there is a polar origin. You will always have a ramp response when you apply a step input torque. Of course, if you make one of these parameters or several of these parameters 0, your system will change, but it's also your system will also change. So that's of course not the purpose of this example, to change the actual system. All right, this was actually for this example, having discussed about a rotational mechanical system. In this case, the complexity was a little bit higher than the first example about the rotational mechanical system. We have seen that this is a fourth order system because we have 2 inertias, 2 dampers, and also 1 spring, so that will cause that the system is a fourth order. And we have also seen what kind of a response we will get when you apply a step input. So we've worked out everything step by step from the differential equations, going to the Laplace transform, and also worked out step by step towards the transfer functions G1 and also the G2. All right. If you have any questions, comments about this example, please let me know and I will try to answer them as soon as possible. Don't forget to like and share this video so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time. Take care.